Hello, we are the Team 26 Cleanup Bot crew of the Embedded System Design class. And today I'm going to show you a revolutionary new idea. Is the Roomba just too circular for you? Is it too efficient? Do you have lines placed in your house conveniently and an incinerator in the corner? Then do we have the products for you? The Cleanup Bot. Revolutionary new square design. Treads to get all over your house. Everything you need to clean up your life.
So, for our revolutionary cleanup bot, we use a rover that connects itself to a computer to obtain the algorithm to move around your room and make it sparkly clean.
So our rover uses sensors to follow a grid. It goes down, cleans each row, pushes it in the corner into your incinerator.
So in this next section, we'll talk about the algorithms we used on the Raspberry Pi. Pi. Oh yes, this one of course. Yeah, so for the algorithms we used on the Raspberry Pi, we set it up in 5 different states. The first one was used for scanning and searching for all the trash and pushing it to the opposite end of the grid. The second one was used for reversing, to return itself to the scan state to return it to the original line. The third one was to clean the final row when it was done running through all the rows for trash. And then we had the sweep command, which just ran through the end and pushed it onto the incinerator. Once it was done with that, we executed it into the end mode, where it just stopped action and waited for retrieval later. So, for how the Pi actually goes out and decides on what to do with with the red sensor data, is it takes the information, depending on the location, and tries to use that to decide on where it is and what it actually needs to do next. For example, with the 8-bit from it read from the IR sensor, it would decide whether it's the 2 middle ones to go forward, or if it's all the ones on the left to try to turn left. This could be widened for a larger amount of numerals so that it can cover more cases, but currently it just takes a few values in its coverage range and tries to deal with it that way. What we have to try to fix this for now is currently pretty much a self-correcting algorithm where it will just try to go and fix itself upon the line if there's any issues, with small adjusts and a continuation to do so even if there isn't really anything there, based off of the inherent ability to just try and implement the previous movement command, whether it's forward, reverse, or if it's just left or just right.
Now let's move on to communications. The first place we're going to start is sensors. The sensors has its own thread. Once the sensor gets the piece of data, it sends it to the rover, which then sends it through the Wi-Fi on UART to the Raspberry Pi. Now the Raspberry Pi is going to take the data and it's going to interpret it. It'll determine if it should turn or if it should be going straight, maybe reverse, anything like that. If it has to change course, it'll send me back through the Wi-Fi, which then I'll take it, interpret the data, and send it off to the motors through another queue for the motors to execute. When I get the confirmation that the motors has executed, we will go back to the sensors, waiting for the next piece of data. This will all take about 100 milliseconds, which is plenty of time to go through the whole cycle.
We decided on an 8-bit array of digital IR reflectance sensors. And so what they do is there's an emitter and receiver LED pair, and each one will output the LED and then time how long the reflectance takes. So it could take anywhere from less than a millisecond up to about 10 milliseconds. We had a ultrasonic distance sensor. So what it does, it uses high frequency sound waves, bounce off the target and reflect. And to get that data to the board, it sends it over the UART, which sends 4 bytes of predefined data, and it actually sends millimeter data to the board. And so that data can range from 300 millimeters all the way up to 5,000 millimeters, which is pretty far for our range.
The rover itself consists of 2 independent DC motors controlled by the motor shield, which is this third shield up here. There's 4 pins that you need to set in order to control the motors. There's 2 enable pins and 2 directional pins. On the motor shield, that's pins D0, D1, D5, and F1, and that translates down through to the MAX32, D1, D0, C14, and G1.
For our initial project requirements, we decided on 2 IR sensors to follow the lines. So we would have one on the front and possibly one on the side or in the middle. And then for the distance to detect objects, we decided on an ultrasonic sensor that would just be mounted on the front, and it would send a pulse to check if there was objects in front.
For the motors, we wanted them to be able to respond to commands from the Pi, as well as include a manual mode that would enable the user to use WASD directional keys to control the motor manually. And we also wanted to be able to use the motor different speed capabilities to be able to push an object differently based on how heavy the object was.
Additional requirements include having a separate thread for each core piece of the rover. There is a Wi-Fi thread, a sensor thread, and a motor thread. The sensor thread sends its data to the Wi-Fi thread, which then sends it through the Wi-Fi to the Raspberry Pi. The Raspberry Pi then interprets it, sends it back, and then it goes to the motor thread through the Wi-Fi thread through another queue. Each of these has a blocking method so that it is ready to receive the next piece of data.
The final part of our original design dealt with the Pi. We used the Raspberry Pi to essentially deal with any algorithmic needs to decide on what the rover would actually do. This would be divided out into various different cleaning states, which would control the behavior that would be needed to actually run the rover in general. On top of this, we desired a UI component that would display feedback and would also allow for manual control.
During implementation, we ran across the issue of robustness. As for component failure, we didn't really account for it, though if the sensors were to quit working, the robot would just stop in place and it wouldn't actually receive any more instructions from the Pi. As the sensors go, with the mounting that we had, we didn't really have any problems with incorrect readings at all. But for ultrasonic, when we started to implement, we ran into issues with the data only sending once, and then when we told it to read again, it would never actually send the information back. So we had to scrap the ultrasonic sensors.
When it came to our actual implementation of our system, we ended up having a few hiccups, but for the most part, it followed what we desired from the start. For example, the communications between the rover and the Raspberry Pi did work, without many issues at all, though it did cause a few other issues elsewhere. And the logic on the Raspberry Pi also didn't have issues at all, since it worked out perfectly in simulations, and also worked out when everything was lined correctly. The communications were essentially dealt with from the Pi side as well, without many issues, using Pi Serial, a library that we found online to help us with this process.
Implementing the motors hit a snag when we discovered that any code involving any of the motor pins being set would stop running on the rover when the Wi-Fi shield was attached. For an unknown reason, moving port G and initializing it to output separately from the rest of the port stopped this problem, and we still don't know why. In the end, both direct pin setting and pulse width modulation were implemented for the motors, although we did not use pulse width modulation in our final product.
Although the ultrasonic worked well in individual testing, when we went to integrate with queues, we ran into problems where it would only send the data once, and then once we told it to read again, we actually wouldn't get anything back, so we had to scrap the distance sensing. During integration, we didn't have to add any robustness for component failure, and it never really came up as an issue. Though with the sensors, if they were to stop working, the rover would just continue to do its last command. With the hour sensor, the readings were consistent due to the strong mounting of the sensor to the rover.
The biggest problem for our implementation with robustness had to do with what happened when the rover had slanted orientation. It meant that the movement would essentially go off into the distance off the table, or it would just go and try to find a line that was incorrect. This was a problem for obvious reasons and needed correction. This not only gave problems to just movement, it also made it so that different readings could be given from incorrect orientation, giving incorrect values for returned commands. The combination of all these problems had it failing from time to time and was a problem with robustness. This, mixed with the fact that some movements were incomplete based off of the actual physical implementation, meant that we had to fix it through some means. What we did to fix this was implement self-correction code. This code checked various side values to make sure that it was correct and that it could just adjust itself with small left and right adjustments to make sure that it was aligned correctly with the center path for moments where it needed to be. It even checked for cases where it would align itself right before turning, or cases where it needed to go and search for lines if it was ever off a line. This ended up giving our rover a deep level of consistency, which made it almost never fail when just running normally.
The first major improvement would be to get the ultrasonic sensor to work. If we could have gotten that, then we would be able to discern whether we should or should not clean up a row. This would make our rover smarter and thus have to clean less rows in the overall code. Adding more redundancy in checks for different read data would also improve the accuracy, as it wouldn't deviate from the path quite as often. We could also re-implement the old code that dealt with the smarter movement and deal with some of the minor issues with reads. This would allow us to fix some of the other issues since the old code was much more consistent. And the physical construction of the grid. The physical construction of our current grid was kind of small. If we would allow it to become bigger and with more space, maybe even more rows, we could show the full range of what the rover could do.
As you can see with the initial state with the rover, it is first set to scan, and what it does in that mode is to check for trash and push it off the end. After it pushes the trash off the end, it goes into reverse and returns itself to the original line and then returns to scan.
For the convenience of the pi algorithm, we turned the manual motor state's turns into 90-degree time turns. So that way, when the rover comes across a turn, it can turn in a way that allows it to be almost completely lined up again with the sensors on the middle of the line. In order to keep the sensors in front of the rover at all times, we decided to complete a 180-degree turn when we finished reading a line. And we did the same timing as the 90-degree turns to ensure that the rover is once again centered on the line. In addition to the time turns, we also made 2 adjustment turns. These turns are called when an incorrect value is read on either side of the 2 center IR sensors. That way the rover is able to quickly adjust itself and get back to the middle of the line. These adjustment turns take precedence over any other command from the Pi. Also, we found that when placed anywhere on the grid, the rover was able to manipulate itself to the center of any line using these adjustment turns.
When it reaches the end of the final line and changes its state from scan to reverse, it sets a flag so that when it returns back to the main line, it will go and turn right, executing the clean state instead of going back to the scan state. With this, it will circle the perimeter and go around to clean up the trash and put it all into the corner to finish our algorithm.